Welcome to this tutorial on distributions of the sample means. In this session, we will explore how the distribution of sample means changes with different sample sizes, and how it leads us to one of the most powerful results in statistics, the Central Limit Theorem. Through examples, simulations, and visualizations, we'll see how sample size influences shape, spread, and accuracy in estimating the population mean. We have k samples, each containing n observations, drawn from a population with unknown mean mu and standard deviation sigma. From each sample, we calculate a sample mean, denoted x bar 1, x bar 2, and so on, and a sample standard deviation, denoted s1, s2, s3, etc. To estimate the population mean, we take the average of all the sample means. This is called mu hat, and is calculated as x bar bar. To estimate the population standard deviation, we find the standard deviation of the sample means and multiply it by the square root of n. This gives us sigma hat. The Central Limit Theorem, CLT, states that regardless of the shape of the original population distribution, the sampling distribution of the sample mean, called x bar, becomes approximately normal as the sample size increases. In the image, this idea is demonstrated visually. The first row starts with a skewed distribution. As sample size increases, the distribution of x bar smooths out and becomes more normal. The second row starts with a uniform distribution, again showing how larger samples result in a sampling distribution that closely resembles a normal curve. This theorem is widely used in real-world applications, like hypothesis testing and confidence intervals, because it allows statisticians to make reliable predictions about a population, even when the original data isn't normally distributed. As the sample size increases, the spread of the sample means decreases, resulting in a tighter and more concentrated distribution around the population mean. The mathematical equations explain key concepts of the Central Limit Theorem. First equation, x bar, x, equals e of x bar, showing that the sample mean is an estimator of the expected value of the sample mean. This equals the sum of all observations divided by n, which simplifies to mu, when each observation has the same mean. This confirms that the sample mean is an unbiased estimator of the population mean. Second equation, the variance of x bar, sigma squared, equals the variance of the sample mean. It is calculated as the variance of the sum of n observations divided by n, which simplifies to sigma squared over n, sigma squared, n, when all observations have the same variance. Third equation, the standard error of x bar, sigma, equals sigma divided by the square root of n, sigma, square root n. This represents the standard deviation of the sampling distribution and shows that the variability of the sample mean decreases as the sample size increases. Final equation, the estimated standard error, s, is calculated as s divided by the square root of n, s, square root n, when the population standard deviation is unknown. Here, s represents the sample standard deviation. These equations show how sample statistics relate to population parameters and how larger sample sizes improve the precision of estimates. The following slides further explain the Central Limit Theorem with dice-throwing experiments and plotting the outcomes. R language is used to conduct the experiments and plot the outcomes of the experiments. This slide explains the sampling distribution of the mean using the example of a fair six-sided die. The die is assumed to be thrown infinitely many times, and the number of spots on each throw is represented by the random variable x. Each outcome from 1 to 6 has an equal probability of 1 by 6. So, the probability distribution of x is uniform. The mean, or expected value of x, is calculated by multiplying each value by its probability and summing the results. This gives mu equals 1 times 1 by 6, plus 2 times 1 by 6, and so on up to 6 times 1 by 6, which equals 3.5. The variance is calculated using the squared difference from the mean, weighted by the probabilities. This gives a variance of approximately 2.92. The standard deviation is the square root of the variance, which is approximately 1.71. On the right side, the same calculations are implemented in R code using the Roldi function and basic plotting and summation commands. This example shows how the mean and standard deviation are derived from a simple probability model of rolling a fair die once. We are analyzing the outcome of a single roll of a fair six-sided die. Each face, from 1 to 6, has an equal probability of 1 by 6. This creates a uniform probability distribution, where every outcome is equally likely. Using this distribution, we calculate the mean, or expected value, by multiplying each face value with its probability and summing them. The result is 3.5. Next, we calculate the variance by taking the squared difference between each value and the mean, multiplying it by the probability, and summing the results. The variance is approximately 2.917. Taking the square root of the variance gives us the standard deviation, which is about 1.708. Since we are rolling the die only once per sample, the distribution of sample means is exactly the same as the original uniform distribution. In this case, the central limit theorem does not apply. To observe the central limit theorem in action, we would need to roll the die multiple times per sample and then analyze the distribution of the average values. This slide explains the sampling distribution of 2 dice. We consider all possible samples of size 2, that is, rolling 2 dice at a time. Each sample consists of a pair of numbers, and for each pair, we calculate the mean of the 2 values. Since there are 6 outcomes for each die, there are a total of 36 possible samples. These are shown in the table, along with the calculated sample means. Even though there are 36 samples, the number of distinct mean values is only 11, ranging from 1 to 6 in steps of 0.5. Importantly, some means occur more frequently than others. For example, a mean of 3.5 appears often, while means like 1 or 6 appear only once. This demonstrates a key idea. When we take multiple samples and calculate their means, the distribution of sample means tends to cluster around the center, forming the basis of the central limit theorem. The slide presents the sampling distribution of the mean when rolling 2 dice. It includes a table listing possible values of the sample mean and their probabilities, along with a histogram that visually represents the probability distribution. Additionally, the slide contains formulas for calculating the mean and variance of the distribution, with computed values. This slide presents an analysis of rolling 2 dice and the probability distribution of the outcomes. On the left side, there's our code that calculates probabilities, the mean, and the standard deviation. On the right side, a graph visualizes the probability distribution, displaying probabilities for the averages of the outcomes ranging from 1 to 6. The slide offers a statistical breakdown of dice roll results. The distribution of the sample means is symmetric about the mean of the means, which estimates the population mean, of 36 outcomes. The image presents a statistical analysis of rolling 3 dice. On the left, there's a script in R that calculates the sampling distribution of the average dice rolls. On the right, a plot visually represents the probability distribution of the mean values obtained. The title, Sampling Distribution of 3 Dice, is displayed at the top. The slide illustrates the central limit theorem using the example of rolling 3 dice. It contains our code, a table of computed values, and a probability distribution plot. The theorem states that as sample size increases, the distribution of the sample mean approaches a normal distribution, regardless of the original population's shape. The slide highlights this principle with formulas for calculating the mean and standard error, showing how variability decreases as more dice are included in the sample.